This is a picture of the night sky captured using a radio telescope. It looks like a normal sky full of stars, but every single dot you see here isn't a star, it's a galaxy. Those cloudy patches to the left are supernova remnants. Now look at this picture. It's an optical image of the galaxy Centaurus A. This is its radio image. We can see powerful jets of charged particles shooting out from the supermassive black hole at its center, stretching millions of light years. Looking through radio telescopes lets us see what's otherwise invisible. That's because they collect light from a very specific part of the electromagnetic spectrum called radio waves. What we normally see is just a tiny part of this spectrum, the visible light our eyes can detect. For most of human history, that's all we explored. The sky at radio wavelengths isn't limited to stars. It's filled with galaxies, pulsars, nebulas, and even black holes. So, where exactly do these radio waves come from? And what can they tell us about the universe? The first radiation released after the Big Bang has been stretched over time so much that only radio telescopes can detect its long wavelengths. By studying this radiation, we can see what the young universe looked like 13.8 billion years ago. In the moments after the Big Bang, the universe was extremely hot and dense. Light and matter were tightly coupled. It took about 300,000 years for it to cool enough for atoms to form, allowing light to travel freely for the first time. This is the cosmic microwave background radiation. This radiation is the farthest and oldest light any telescope can detect. We can't see beyond it because before this moment, the universe was completely opaque. The CMB is the closest we can get to observing the Big Bang itself. To study signals like these, we need incredibly sensitive telescopes. Most radio telescopes use large parabolic dishes that can be aimed at any part of the sky. The strength of these signals is extremely small compared to visible light, so to gather more data, we need larger dishes. The bigger the dish, the more we can detect, and the deeper we can see. Building a single telescope large enough to get that level of detail would require a dish tens of kilometers wide, an almost impossible engineering challenge. The largest single-dish radio telescope ever built is in China, with a diameter of 500 meters, and even that is nowhere near large enough for such observations. Instead, scientists found a more practical solution. They discovered that by combining the signals from multiple smaller telescopes, they could achieve the same resolution as a much larger dish. This technique is called interferometry. One example is the Very Large Array in New Mexico, which uses 27 individual dishes. Together, they function like a single instrument larger than New York City. Now imagine them spread across the entire planet, all working together as one. That's exactly how astronomers captured the first image of a supermassive black hole. The Event Horizon Telescope, a global network of observatories, achieves the resolution of a telescope the size of Earth, sharp enough to read a newspaper on the moon. Radio telescopes don't just look at the farthest reaches of the universe, they also help us understand our own galaxy in extraordinary detail. Hot stars emit all kinds of electromagnetic radiation, including radio waves. But most of the radio signals we detect in our galaxy don't come from stars. They come from the vast clouds of hydrogen gas that fill interstellar space. But why does hydrogen emit radio waves? A hydrogen atom consists of a proton and an electron, each with a property called spin. When their spins are opposite, the atom is in its lowest energy state. In the cold regions of space, most hydrogen atoms remain like this, but collisions with other particles can flip the spins into a higher energy state. When they flip back, the atom releases energy as a radio wave with a wavelength of 21 centimeters. Radio telescopes can detect this signal as a thin line stretched across the Milky Way. The densest hydrogen regions mark the birthplaces of new stars. By observing how the signal shifts as it moves toward or away from us, astronomers can map the galaxy's rotation. When this velocity data is combined with signal strength, it reveals the spiral pattern of the Milky Way. That's how we know our galaxy is a spiral. But hydrogen waves aren't just used to study galaxies in interstellar clouds, they're also used to listen for signs of intelligent life. Because hydrogen is the most common element in the universe, the 21 centimeter line is considered a kind of universal broadcast frequency. Any civilization with radio technology would likely know this. Since the 1960s, astronomers have tuned their receivers to this frequency, listening to nearby sun-like stars for any artificial signals. In 1977, a strong, unexpected signal was detected by the Big Ear Telescope in Ohio. It lasted 72 seconds and was so unusual that astronomer Jerry Emmons circled it and wrote "Wow" on the printout, now famously known as the WOW signal. It appeared to come from the constellation Sagittarius, and we haven't detected any unusual signals since then. Perhaps the most fascinating thing is that these telescopes can detect molecules like water and complex organic compounds in interstellar space. Just like hydrogen, every atom and molecule rotates and vibrates in its own unique way, producing radio waves at specific frequencies. A radio spectrometer splits these signals into their individual frequencies. Astronomers then compare them with laboratory data of known molecules to identify exactly which molecule is present. Astronomers have even found sugar molecules around a young star like our Sun. It was the first time sugar was detected in such an environment, showing that the basic ingredients needed for life can already be present when new planets are forming near a star. Today, about 70% of what we know about the universe comes from these telescopes. They scan the sky day and night, picking up faint signals that help us understand our place in the universe. And with every signal, we learn a little more.